Okay, so as we just saw, behavioral cloning is not the most robust way. It's not a robust way to perform imitation learning. So let's look at other approaches that might allow us to do robust imitation learning. So in behavioral cloning, the learned policy might encounter states that weren't visited by the demonstrator. That is, they are not in the demonstration trajectory, which, as we just discussed, might lead to catastrophic collapse in performance. So an easy way to address that would be to, instead of minimizing the loss on the states that were collected, or the demonstrator state distribution, we would like to minimize our loss on states that come from the trained policy distribution, right? So yeah, minimize the state or learned policy, right? So instead of doing argmin on the state actions loss coming from the demonstrator, we'll try to minimize the loss, the same loss, for states coming from our trained policy. So hopefully this will result in much more robust imitation learning. However, this requires us to add an assumption that we can actually ask the demonstrator about those states that we encounter while running our policy, the policy that we're training. More than that, this will already be some type of an online procedure, right? We'll have to go to the environment and collect new states and then train on them. To be an iterative procedure. So indeed, we can get more robust training by using interactive imitation learning or direct imitation learning. We use the interactive demonstrator to shift from minimizing the loss for the state action pairs under the demonstrator distribution to those coming from our trained policy distribution. Okay, so this is what I said just a minute ago. And as I said, we add the assumption that we can query the expert at any state. So we can collect new states and ask our demonstrator, PyD, what is the action for that state, or what is the suggested action for that state. So the key thing here is to sample trajectories using the policy that we are training, right? And of course, this policy evolves over time, but each iteration we do use the policy in order to collect trajectories. Then we evaluate the loss on the sample trajectories, on the new states coming from our trained policy. So how can we do this process, this iterative process? So let's just start with a naive attempt, right? A straightforward way to do it. We'll simply repeat. We'll train our we're going to collect states, right, from the state distribution produced by our current policy in iteration I. Right, we'll do it in iterations. And then we're going to update our policy to minimize the loss on these states that we just sampled, at iteration pi. Sorry, okay. What's the problem with this? This actually does not work very well. Because this might lead us to oscillating policies. It's not guaranteed to converge. You don't have convergence guarantees for this process. And let me show you a very simple example. So let's say that our first policy that we are training, pi0, theta 0, is not driving on its intended lane. Let's say that we are trying to learn to drive on the right lane here. Apologies for the Indians in the audience. We'll drive on the right side. And let's say that our current policy actually has a bias to go left. So of course, the demonstrator will take all of these states along this trajectory, and the demonstrator will say, hey, go more to the right. Apply actions that are more to the right. Okay, and then we'll train our policy, and at time step at the policy 1, the next policy, or I+1, we'll have a policy that actually has a bias towards turning right. Again, we'll ask our demonstrator, what should we do in these states? And we say, well, you should go more to the left. But this might lead us back to this situation, right? So this simple implementation, this simple approach might oscillate between policies. Well, this is not what we would like to do. How can we address this issue?
Train on all the data?
Data aggregation.
Yes.
Right, yes. So yes, there's a very simple way to address this, and this will be data aggregation. So instead of minimizing the loss for the states that we observed just in the last episode, or the last iteration, we'll minimize the loss for all of the states that we observed also throughout the previous history. This is known as data aggregation. Okay, data aggregation, or the resulting approach is known as dagger. And this is again in the same paper by Rosatel in 2011. So they write in the paper, dagger proceeds by collecting dataset at each iteration under the current policy and trains the next policy under the aggregate of all collected datasets. Okay, so it's a simple fix. We just minimize the loss over all of the previous data. It trains a deterministic policy that achieves good performance guarantees under its induced distribution of states. What are good performance guarantees? So we'll discuss those in a second. Okay. Collecting dataset at each iteration under the current policy and trains the next policy under the aggregate of all collected dataset. Okay, this is just a repeat of what I said before. So this is the pseudocode for dagger, for the improved iterative approach to training using an interactive demonstrator. And you will see that there's also some extension to the general framework that I showed you before, where one important point is that the data collected at each iteration is not just by pi I, which is the policy in iteration I, but it is some linear combination between pi I, the policy that we are training, and also the demonstrator policy, given here as pi star. Why is that? So this is more of a practical implementation detail, and so I added the text here explaining this point. To better leverage the presence of the expert in our imitation learning setting, we optionally allow the algorithm to use a modified policy, right? This is known as pi I. So this is the pi I, and pi hat I is the one that we're training. Pi I is the linear combination of pi hat I and pi star. That queries the expert to choose controls a function of the time while collecting the next dataset. What? Well, it's just a linear combination of the two, right? And of course, this linear combination, they say optionally, just because, of course, this is controlled by the beta parameter here. So you can set beta to be 0, and then you don't have any combination, or you can increase the strength of relying on the expert. By the way, you can see that beta is also varying. It changes with or it could change with iterations, right? Intuitively, let's ask Vaibhav, let's see if he knows. Intuitively, what should be the initial beta and the towards the end? How should it change over time, over iteration?
Initially closer to 1 to give the demonstrator more preference. And as we learn from the demonstrator samples, we can give more control to the RL policy. I mean the IL policy, the training policy. Yeah.
You get full score. Good job. Yes, that's correct. So again, this is from the paper. They say the first few policy with relatively few data points may make many more mistakes and visit states that are irrelevant as the policy improves. So this gives you a hint that probably at the beginning you should use a beta that is closer to 1, meaning rely more on the expert, and as you progress, maybe decay it.
In RL, we have a lot of exploration requirements, but over here it seems they do not want to explore many states. Does exploration help with Dagger?
So exploration is not relevant here because we're not trying to find a policy, right? We're trying to imitate as closely as possible the expert. We don't require to cover the entire state action space. We don't require to infinitely visit each state action pair. If we can perfectly imitate the demonstrator, that's all we can do supervised learning. Then we don't care about the other state space. The goal here is much simpler than the goal in RL. Or, let's say, training the policy on the goal here is a simpler process than training on the RL goal.